Welcome to the exam 2 review. Today we're going to be going over just basically everything I think you should know about the exam. And I thought it would be beneficial to go over everything you should know for the midterm in my opinion. So starting off, I'm going to go over what a carbocation is and what the most stable form consists of. So methyl is going to be your least stable, then it's going to go primary, then it's going to go secondary, then it's going to go tertiary. And if you draw this out, this is what this one would look like. This is what this one would look like. This is what this one would look like. And then your tertiary would look something like this. So send that, that's what that looks like, that's what that one looks like, that's what that one looks like, and that's what that one looks like. So besides this, resonance also plays a role in stability and also ring expansions. So for example, if we have a compound that looks like this, versus a compound that looks like this, this is the more stable carbocation, and that's due to the resonance that can occur right here. Because this electron can move down, and it can then lead to a product that would look like this. And that positive charge can be resonate all throughout the structure. So due to resonance and also number of carbons around the positive carbocation, from a distance, however, anything to the right of carbon can also destabilize the charge. So we have to keep that in mind. So on the periodic table, the organic periodic table, if it's from a distance and it's to the right, it can actually destabilize the carbocation due to an inductive effect. So that's actually bad. We don't want that to happen. I'm going to show some examples now of this happening. So if we have a structure that looks like this, compared to a structure that looks like this, which is actually less stable than a structure that looks like this. So this would be your most, this would be your second most, and this would be your least. And this is your least because of that inductive property that happens with the fluorine. And right here, the fluorine can actually, once again, perform resonance, and this charge could move up here. So another example of resonance that is super important to understand is benzylic compounds. So let's take a look at some of those real quick. Benzylic compound that can actually act in stabilizing a carbocation would be one like this. Let's take a look. So if we have a benzylic compound and we have a positive charge right here, this is actually less stable. Oh my bad. This is less stable than a compound that looks like this. And that's due to resonance being able to occur right here, which could then transfer this positive charge all throughout this benzylic compound. And that can't happen here. Now, we're going to go over hydride shifts and stuff that can occur to make this more stable. And what could happen here in order to make it more stable is a hydride shift could occur, and this compound could then turn into a compound that actually looks like, after that hydride shift, something that looks like this, meaning these two are now equal. So the next thing to understand when dealing with carbocation stability is ring expansion. So here's a few rules of thumb when it comes to ring expansions. 3 to 4 does not happen. 4 to 5 happens, that's good. And then 5 to 6, that's a maybe. There's no real stability improvement from a 5 to a 6. So it will happen, it can happen, but it's not a necessity because there's no real carbocation stability improvement from a 5 to a 6. So these are the ring expansions, and we're going to go over some examples. So the first example we're going to go over, write this out real quick. Is if we have a compound that looks like this, we can have a ring expansion occur, which would then make it look like this. But this is still not your most stable carbocation because once again we can have a hydride shift occur, which we haven't talked about yet, which could then attack here. And this could then turn into a compound that looks like this with your tertiary carbocation. So that's the most stable carbocation from this ring expansion. Another example that we can do is one that looks like this. Now, would this undergo ring expansion or not? This would not undergo a ring expansion. And that's due to this being a three-membered ring, and we never go from a three-membered ring to a four-membered ring. So all that's going to happen here is, once again, we got our hydride shift, and this would then turn into something that looks like this. That's all that would happen here. And that's due to this being a three-membered ring, and three-membered rings never go to four-membered rings. So now that we understand all of that, let's shift gears and look at hydride and methyl shifts. Hope you catch the pun there. If possible, these will occur for some additions, E1 and SN1. So let's take a look at some of these. So the first one I'm going to start you off with is a hydride shift, which I already kind of showed you in a couple examples of that in the past examples. So let's just look at a few more. So a good one would be something like this. Now, in order for this to become tertiary, so we want to go from 2 to 3 here. And another thing to note, only occur if carbocation becomes more stable. So these will only occur if the carbocation becomes more stable. They just won't randomly occur. You can't just have a hydride shift or methyl shift occur. There has to be some form of increased stability. So what's going to happen here is I'm going to draw in the hydrogen right here, and this hydrogen is going to come over and attack, and that's going to give us this product right here, which is more stable than our original product. Now, methyl shifts follow the same mechanism, except instead of shifting a hydrogen over, we're going to shift a methyl over. So let's take a look at that. So a good example of that happening would be something like this, and then this would come over, and this would leave us with a tertiary carbocation, which is more stable than our secondary carbocation. So let's use an example, an actual reaction occurring with this. So let's say we have Br, and let's just say Br leaves. That would give us a secondary carbocation. However, that's not our most stable carbocation. So then what could happen is our hydrogen could shift over, and then once that happens, boom, tertiary carbocation. And then just for the heck of it, let's say the bromine comes back in because it's still just floating around and attacks, and that would form a product that looks like this. So let's do another example here real quick. Let's clear the page. Let's go something that looks like and let's just say let's just say Cl minus this time. So what could happen here is bromine could leave, and no, actually this isn't a good example, my bad. Let's just say the bromine reattacks just to show the carbocation in the hydride shift. So it would leave us with something like this. And then what could happen here is you have a hydrogen shifts over. That then leaves us the tertiary carbocation, and then say it reattacks. This isn't a real reaction occurring, I'm just trying to show the mechanism that occurs with these shifts. And then you'd get the product. Okay. So next thing we should go over is SN2 versus SN1. And this is a very important skill for any upcoming exam. So if we take a look at this, let's clear the page here. SN2 versus SN1. And I've come up with a little graph or chart, if you would say, that helps me determine between the two and what the two would do. So for SN2, I know that SN2 likes primary and methyl. And SN2 likes a strong nucleophile. It does backside attacks, dislikes sterics, likes polar aprotic solvents, and it has no rearrangements because it is a unimolecular reaction. And its energy diagram looks like this. Now then an SN1 reaction is a little bit different. It likes tertiary carbocations. That's its favorite. And it likes sterics. It likes polar protic solvents. It likes weak nucleophiles. It does carbocation rearrangements, and it likes resonance. So the more stable the carbocation, the better for SN1. And these can both undergo in a secondary carbocation. And the graph for this one is going to look something like this, because it's a unimolecular reaction, meaning there's more than one step occurs. SN2 is bimolecular, meaning it all happens at the same time. So when determining between SN1 and SN2, I like to go in this order if it's secondary. So this is if it's secondary. If you still can't determine after all those rules what it is, I like to go in this order. Let me erase all this, and let me write these rules out for you. SN1 versus SN2. So the first thing you should look at, of course, are your sterics. Second thing you should look at is the nucleophile that's being utilized in the reaction. The third thing you should look at is a solvent. And the fourth thing, I mean, it very rarely ever comes down to this, but if it does, look at the leaving group. let's now look at what makes a good nucleophile, just so we can look at that second step, because we already went over the sterics. So, nucleophilicity. So, there's a few things to remember for what makes a good nucleophile. Basicity. Spelled that wrong, but you guys get the drift. And the more basic, the better the nucleophile. Next one is charge. Good nucleophiles have negative charges. They're not neutral compounds. They usually have some, and they have a negative charge. That's the best way to remember that. Third thing is sterics. So my bad, did not mean to put that. The less sterics, you want it to be like a missile. And now then, another thing to keep in mind is the atom itself. And if we draw out the periodic table, going this way is better, and going this way is better when it comes to nucleophilicity. So, now that we have that under our belts, now let's take a look at solvents. So we have two types of solvents. We have protic and aprotic. So let me see. So protic solvents are going to be things like OH based, so like ethanol, methanol, stuff like that. You also have H2O, you have acetic acid, and you also have ammonia, which is NH3. So those are going to be your protic solvents. Now then, when it comes to your aprotic solvents, it's basically these. So if it's not any of these, it's most likely an aprotic solvent. But these are the ones you're probably going to come in contact with. So you got CH3CN minus. Did not mean to do that. CH3CN minus. You have acetone, DMS, DMF. Trying to think of any other ones. Yeah, those are the ones you're going to run into. And if it's none of these over here, because there's very few protic solvents, it's most likely going to be an aprotic solvent. But those are the ones you're going to run into on the exams. So now that we have those under our belt, let's take a look at leaving group ability. This is a very important thing to understand for organic chemistry and organic chemistry classes in the future. So leaving group ability. Oh, crap. Spelled leaving wrong. My bad, guys. So leaving group ability. The better the leaving group, the faster it leaves. So for example, BR, great leaving group, leaves quite fast. Fluorine, not a very good leaving group, does not leave at all. But let's look at a little chart I've devised for leaving group ability. So 0, you have H3O plus great leaving group, -5. You got H2SO4, good leaving group, -7. You got HCl, good leaving group. You got -8, which is going to be your HBr or OTS. These are equal. OTS might be a little slightly better of a leaving group. And then -9 is HI. And if you draw these out, the way the arrow's pointing is the better leaving group direction. So, also I should note, when it's a good weak nucleophile on a secondary carbocation, it can go either way, and the solvent is critical. So these include, I forgot to mention this, if it's one of those weak, good nucleophiles and it's on a secondary carbocation, it can go either way, SN1 or SN2. And these good, weak nucleophiles are your iodine, bromine, chlorine, RSH, and those are the ones. And when you're dealing with these, you should know that if it's on a secondary and this is a leaving group, it's going to come down to the solvent. And if it's protic, it's going to go SN1. And if it's aprotic, it's going to go SN2. So now that we have those rules under our belt, let's take a look at some practice problems, just so we can hammer these concepts into our head. So let's say we're giving a compound that looks like this right here. We know that it's going to form a carbocation. That's a tertiary carbocation. We know that this is a bad nucleophile because there's no charge on it whatsoever. And we also know that methanol is going to act as a solvent, which is a protic solvent. So what's going to happen here is this is going to leave. It's going to give us this. And once this occurs, the MeOH is going to attack. And then once that attacks, it's going to give us our final product. And I'm not going to show the proteinization just to save time. It's going to be O. So that's what would happen here. So let's look at another one. Let's look at something that looks like this right here. So this is a little bit more complex of one. Gotta draw it out. I just want to give you guys one of these just so you could use your Newman projection skills, because I think that's going to be a critical skill for the final, maybe even the midterm. Definitely the ACS though. So if you're given something like this, and then it's being reacted with, what I like to do is look at the Newman projection and then translate it. So let's translate this. If we translate this, we got Br down, ethyl up, and then we have bromine pointing down. We have methyl pointing out. We have hydrogen in the back. We have on the back side hydrogen, and then we have methyl. And if we redraw, just bring this down. Now we can tell what the product's going to be, if it's SN1 or SN2. We know this is a good weak nucleophile. We know this is an aprotic solvent. And when we leave, it's going to form a secondary carbocation because the methyl is actually going to act as another carbon. So this is definitely going to be an SN2. So what's going to happen here is the bromine is going to leave, chlorine is going to attack at the same time. It's going to do a backside attack. When it does that backside attack, your final product is going to be something that looks like this. And that's your final product for this one. Let's take a look at another one. So our next practice problem we have is something that looks like this. Draw this out real quick. So, what's this going to do? Well, this is an ionic compound right here. So the Cn minus actually has a negative charge on it. And actually what I'm going to do, just so you guys know, Here's a little tip to know if it's an ionic compound. If it's any of these attached to the compound itself, it's going to have a negative charge because these create ionic compounds because they are metals. So these on top of a nucleophile will make it an ionic compound, meaning that the nucleophile then has a negative charge. So now then, let's do this all out. So what's going to happen here is, since it's SN2, it's going to leave. C- is going to attack. Inversion of stereochemistry, however, so our final product is going to look like this. Oh, my bad. I did not mean to put a bromine on there. That's your final product. So the next one we're going to do is going to look like this. Clear the page. I don't like that. Try and draw this so it's a little bit better. So what's this one going to be? This one's kind of a difficult one. All an H plus ever does is it usually just protonates something. So it's going to protonate this OH, making it H2O, the positive charge. And that's a good leaving group. So now then this can actually then leave. And that then leaves us with a secondary carbocation, and it's a protic solvent. So this is going to be SN1. So we're going to have this. However, we then have the ability for an arrangement to occur. All D is a hydrogen with a proton attached to it, so that will act as our hydrogen shift. That's then going to leave us with something that looks like this. And then what's going to happen is our H2O is going to attack and act as the nucleophile, and that's going to give us our final product. I'm not going to show the protonation because I don't really want to, because I think it's a useless step. And this is your final product for this one. And that's an SN1 reaction. So now let's take a look at SN2 versus E2. And one thing to remember with these is a negative charge is present with these all the time. You're always going to have a negative charge attached to the nucleophile when it's SN2 and E2. So when we're looking at this, put this up here to remind you, the best way to go about it is with a chart. So I'm going to draw a chart out for you guys. So at methyl, only an SN2 can occur, and at tertiary, only an E2 can occur. When you're between SN2 and an E2, of course. I mean, SN1 and any of those can still happen, but when we're trying to determine if it's SN2 or an E2, this is the chart to use. So now then, if it's at primary, we got to ask a few questions. Is the nucleophile TBU O- or NDA? And if that's yes, it's going to be E2 kinetic. And if that's no, that's going to be SN2. And now then, if we're at a secondary carbocation, the first thing to ask is the pKa. So what's the pKa of this thing? If it's less than less than 9, it's going to be SN2. And some examples of that would be CN minus this, or something that looks like this. So these would be great examples of nucleophiles that are less than 9. Now then, if we still have to try and determine if it's not less than 9, then we have to ask ourselves, actually I'm going to erase this because I ran out of room. If the pKa at a secondary carbocation is between 9 and 16, then we're going to have to look at the solvent. So, let me erase over here. So what is the solvent? If the solvent is protic, it's going to go E2. And if the solvent is aprotic, it's going to go SN2. And that's what all you have to really remember for SN2 versus E2. That's the chart. And go back and look at the chart when I was erasing stuff because I couldn't fit it all on here. And if you guys actually need me to draw the chart out and send it to you, just message me. But that's all you have to do to determine between those. So I'm also going to go over E1 real quick because I think, it doesn't happen many times, but I'm just going to lump it in here with them. So E1, very rare, very, very specific set of conditions for this to happen. And these conditions include H2SO4 concentrated, heat with an aprotic solvent, or you could have TSOH with a Dean Stark. So those are the only times that E1 actually happen. They're very rare and they have very specific set of conditions. So if you see these, any of these right here, you know that it is definitely an E1 reaction and you're going to have to use the E1 mechanism. So I also want to note the key difference in mechanisms between E1 and E2. So let's look at E2 versus E1 when it comes to mechanisms. So E1, they have a carbocation intermediate. They happen unimolecularly, they're not bimolecular. E2, I drew that bad. E2, no intermediate because they are bimolecular. So these will form the most stable carbocation before occurring, and these won't. Now, another thing that's important with E1 and E2 is Zatsev's rule. So Zatsev's rule states that elimination reactions prefer the most stable alkene if the most stable alkene can occur. However, for E2, that's not always the case. So, for example, let's take a look at Zatsev's rule. E1 will always form the most stable alkene possible E2 prefers to follow Zatzi's rule. However, anti-periplanar geometry is required. So anti-periplanar geometry, let's go over that first before we go any further. So what exactly is anti-periplanar geometry? That's right. Anti-periplanar geometry. Best way to show this is an example. So anti-periplanar geometry means that the leaving group and the hydrogen have to be opposite of one another when it comes to stereochemistry. So if you have bromine here and you have hydrogen here, this can undergo an E2 elimination, and it can form something that looks like this. However, if you had something that looked like this, let's say, oh, my bad. Yeah, let's say this. And let's say you have a methyl here. This cannot undergo an E2 elimination until the bond is rotated. So you'd have to rotate this bond right here or right here in order for the E2 elimination to occur. You can ignore this rule for E1. This doesn't happen E1. Like I stated before, E1 eliminations always prefer the most stable alkene. E2 prefer the most stable alkene, but they can't always form it. E1, they'll always form it. So let's take a look at this. Let's rotate the bonds real quick. So I got methyl down, I got bromine up, I have hydrogen to the left, and I have methyl up, hydrogen to the right, I have methyl to the left. Okay, now if I rotate this, I'm gonna get something that looks like this, because I have to have the anti-periplanar geometry. So if I rotate this way, bromine goes there, hydrogen goes down, methyl goes up, methyl, hydrogen, methyl. And if we translate this, so now let me translate this for you guys. So I got hydrogen down in the front, I have methyl up in the back, I have methyl on a wedge, bromine on a dash, and then I have methyl down, and I have hydrogen up. So what's going to happen here now is, as you can see, I have that anti-periplanar geometry right here. So the bromine could leave if this is an E2 reaction, and the hydrogen could attack, and that would give us our product, which would look like this. And that would be your product if you actually did this all properly. And once again, remember, disregard this. If it's an E1. This only occurs if it's an E2. So now then, let's run through some practice problems relating with E1, E2, SN2, stuff like that. So what I'm going to do is I'm going to clear the page for you guys, and I'm going to draw just some example problems, and we're going to work through them. Because practice makes perfect. It's a benzoic ring, Br. Oh no. Another benzoic ring. So, and then we're gonna react this with ETO. And H2O is going to be our solvent. So we know that this is definitely either going to be E2 or SN2. When this leaves, you're going to have a secondary carbocation, so still SN2 or E2. However, we have this protic solvent right here, which is going to make it want to do E2 instead of SN2. However, once again, we have the hydrogen hidden on a wedge, just like the bromine, so this is not anti-periplanar. So we're going to have to rotate this. If we rotate this, your final product would be, I'm going to abbreviate the benzylic rings for pHs. This would be your final product if you rotated the rings. So once again, I can do these in my head. If you have to, use the Newman projection. The Newman projection will save your life. If you can do them fast, do the Newman projection. I sometimes double check myself, but I can do these in my head. So we're gonna move on. Let's look at another one, another example I have. So I forgot to mention. Well, I didn't forget to mention. There's another instance where Zatsev's rule is completely disregarded, and that would be something like this. So we have no solvent, so terbutoxide is going to then act as a solvent, and then when this leaves, you're going to have a secondary carbocation. So this is definitely E2, because there's no aprotic solvent, and it's a pK between 9 and 16. So it's going to be an E2. We don't have to worry about the stereochemistry, because there is no stereochemistry, so it could eliminate from here or here. However, we don't want to eliminate from here. That's because, like I said earlier, TBO minus is a large bulky base, and that will always do a kinetic product. And the kinetic product always forms the least hindered product. So it's going to actually go here, and that's going to form your final product that looks like this. Hope that one makes sense. Let's move on to another one. So the next example I have, once again, remember, I'm going to abbreviate the benzylic rings as pH. So what's going to happen here is we have TSOH and we have a Dean Stark. So all the TSOH is going to do is protonate the OH and make it OH2 positive. So we know that this is our leaving group actually. That would then give us this. Carbocation. E1 reactions love to do carbocation shifts. So the hydride would shift over, and that would leave us with this. And then we'd still have our pH here and our pH here. And what would then happen here is a rotation would occur to make the most stable alkene. So we would rotate, and while we rotate, we would also do the elimination like this. So now that's your final product would look like this. And since it's an E1 elimination, we always want to form the most stable alkene as our major product. And this is the most stable alkene. So the next thing we're going to go over, and the final thing you should know, is additions and cyclizations. We've gone over E1, we've gone over E2, we've gone over SN1, we've gone over SN2. The next thing is additions, and this is going to be the final thing. And the best way to go over these is just a bunch of practice problems, because there's just a lot of rules to remember. So what I'm going to do is I'm going to write some important notes to know real quick for you guys. This is additions, and then what I'm going to do is put some notes. And the notes you should know is that syn addition care about stereochem and anti additions don't care about stereochem, just like honey badger don't care. I firmly believe that the best course of action for additions is just practice. So once again, I think we're just going to dive in and do some practice problems because there's really not many things to know. They follow a lot of the same rules that SN1 does for carbocation arrangements. Some additions will undergo carbocation arrangements, and when we get to those, I will explain why they do that. But we're just going to start with some practice problems, okay? So the first one we're going to do is bromination, which is just, I'm just going to show it, actually. So, Br2. And all that happens here, and ROH. So all that happens here is this. And then what can happen here is, since there is no regioselectivity, it could go either here or here, so it doesn't really matter because there's no electron deficient difference. So no matter what you do, either way would be correct, but it could go either way. So let's say it goes this way and eliminates this way, bond, and then you would get this. But when that's eliminating, you have to remember that this comes in and attacks here. So then you are going to get something that looks like this. So you'd have your BR, and then you would have your OR right here. And that's all that would happen. And this would be plus enantiomer. And this is a anti-addition. And all anti means is anti adds both groups on same side, and syn adds. I completely screwed that. I messed those up. My bad. I wasn't even paying attention. Anti does not add on both sides. Syn adds on both sides. Anti adds on opposite. So for example, since this is a wedge and this is a dash, it's an anti-addition. Now if they were both wedges, it'd be a syn addition, and that's when the stereochemistry can kind of become an issue. But we'll practice a couple of those. But let's keep going and see what we got. So the next one I got is H2 or D2. For this, H2, this is a syn addition, meaning they're both going to be added on the same side. So we have to look out for that stereochemistry. And since it is on a wedge, we are going to have to put our H's on a dash, meaning our final product would look like this. And those methyls would then pop out. And there is no enantiomer once again because we can't form the other product due to that stereochemistry. So the next one let's look at is, let's take a look at D2. This is the same mechanism as H2. However, here, since there is no stereochemistry, did not mean to draw the double dash or double bond in right there. Since there is no stereochemistry, we can disregard that, and we can know that it has an enantiomer. So let's look at something else. Here's what I'm talking about, where the SN1 rule actually comes into play. For any of those syn or anti-additions, when it's like that, those ones, carbocation rearrangements don't really occur. However, for stuff like this, additions like this, carbocation arrangements can occur. So for acid catalyzed additions, it can occur. So what's going to happen here is this is going to follow Markovnikov's rule, and the hydrogen is going to go where there's more hydrogen, so it's going to go there. If you actually draw it in, I'll draw it in with a red bond so you guys know that that's not a carbon, and that's going to form this carbocation right here. And then what's going to happen is the hydrogen here is going to perform a hydride shift, and that's then going to form something that looks like this, and then Br minus is going to come in and attack and give you your final product, which is this. See how that carbocation arrangement did occur for this one? So another example of this occurring is with this. I draw this one out for you guys so you guys can see another example. And we're going to react this with H2SO4 and H2O. So once again, Markovnikov, come in and grab that hydrogen. Going to form this. And then we want the most stable carbocation. So this hydrogen is going to hydride shift up here. And then once that happens, nucleophile would attack, and that would give us our final product. I'm not going to show protonation. And this would be our final product right here. Okay. So, when dealing with diluted acid catalyzed reactions, it's going to prefer OH over the actual Br minus, Cl minus, whatever you're dealing with. So let's look at a few of those. So if we have something that looks like this, and then it's dilute, what's going to happen here is, of course, once again, Markovnikov, you're going to have this. However, what's going to attack here is not HBr. It's going to be OH because it's in a dilute solution. So that OH is going to come in and attack here, and that's actually going to give you a product that looks like this instead of the Br attached. And this is due to more H2O being present to attack over HBr. However, when it's concentrated, the HBr will be the nucleophile. So I'm going to show you an example of that now. So if you have concentrated HBr and not dilute HBr, it's going to be the HBr again. Or if it's just regular HBr, it is just HBr. So for example, if we have something that looks like this again, and it's HBr concentrate, we're going to form that. Carbocation here, and then the Br minus come in and attack, and that's going to give you your final product. So this is concentrate, Br, not dilute. So dilute, OH, concentrate, actually use the Br minus or Cl minus or whatever it's actually trying to add. So the next addition reaction we're going to take a look at is OSO4. And all OSO4 does is it adds OH groups syn to one another. So let's draw this out real quick. All that's going to happen is your final product is going to be this. It just adds OH groups into one another. That's all that happens. So let's do one more. And once again, since it is syn, stereochemistry does hinder this addition. So when stereochemistry is hindering this addition, we have to remember that it will attack from the opposite side that the stereochemistry is present on. So for this one, all that's going to happen is this. That's all that's going to happen for that one. So let's go on to another problem. And the other problem I have is MCPBA. And MCPBA is a syn addition by itself. However, when it's accompanied by something else, it becomes an anti-addition. So if it's MCPBA alone, just MCPBA, remember that stereochemistry does hinder it. However, if it's by itself, stereochemistry doesn't really matter. So when by itself, stereochemistry hinders. When accompanied by another reaction, it does not matter. So let's take a look at this. Second, let me stretch. Okay. So if we react this with MCPBA, what's going to happen is just MCPBA is all that would happen. All that would happen. And if this was here, then we would have to attack from the side only, and that would then remove the enantiomer. So remember that for this one. MCPBA is a syn addition on its own, but when it becomes accompanied with another reaction or addition, it is not a syn addition. So for example, and I also forgot to mention that RCOH3 is the same as MCPBA. So let me erase all this and let's do another practice problem of this real quick. So let's say we have something that looks like this. And we want to do RCO3H. And we want to then do MEOH. What's going to happen here? Well, you're going to have something that looks like this occur. I'm going to draw out the mechanism. That's plus enantiomer. And then what's going to happen is it's going to form the more stable carbocation. And then when that happens, the MEOH is going to attack. And then when that happens, you're going to get a product that looks like this. Since it's a nucleophile attack, it's going to attack from the back, and it's going to be O-methyl. We're going to skip the protonation step, and the methyl is going to be on there, and then you're going to have OH here. And that's how that one would go down. And for these ones, you can ignore stereochemistry. It's not really going to matter. So let's clear the page. And the next thing we're going to look at is HGOAC. And it's another reaction you may run into. All this reaction does that is special is that the Hg performs an anti-Markovnikov, meaning the Hg will be added anti-Markovnikov. And it then just disappears. It leaves. And no carbocation intermediate occurs here. It's all one-step, super fast reaction. So there's no carbocation shifts or anything like that. You're just going to keep the original carbocation you start with. You're not going to try and make it more stable. So for example, let me type this as HGOAC, and that actually stands for oxymercurization. And let's draw this one now. Say we have something that looks like this. and we're reacting it with HGOAC, MEOH. All that's going to happen here is it's going to take the HG, the HG is going to be here, it's going to disappear, MEOH is going to come and attack. Remember, it doesn't form the more stable carbocation because it's such a fast reaction, and you're going to get a product that looks like this. And once again, the HG disappears, just like the mental health of every student taking organic chemistry. So moving on, another example of oxymercurization I'm going to show you is this example right here. So all that happens here is, let me put H2O, is once again that HG would be added here, and then the OH is going to be added here. So then it's going to give you product that looks like this. And then plus the enantiomer. That's all that would happen here. And you wouldn't even have to really show stereochemistry for this one. I mean, you can, but no real sense. But that's what would happen for the HUAC with that H2O. So the next addition is BH3. BH3 is another syn addition. So we got another syn addition, or this could be D3 and these are syn additions, and it's going to add an H and an OH syn to one another. So let's take a look at a few of these real quick. So the first example I have for you is one that looks like this. And all that's going to happen here, the reaction's a shit show, so I'm not going to show the mechanism, but just know, not my bad, that's the H gets added, anti-Markovnikov, so the OH actually goes where it's on a less stable carbocation, so this would be your product, and then plus the enantiomer. So just remember that the special thing about this is it's a syn addition. The H and the OH is what's added, unless it's BD or BD to D6, then it's D instead of H's. And all that happens is that's special about this is stereochemistry matters, and the H will actually go where the more stable carbocation is, and the OH is going to be where it go where it's the less stable carbocation is. So that's the only special thing. So just remember that and you'll be good for these. But I even have another example just to nail it in your head. So the next example I have is one that looks like this. DHF. Let's say we react it with H2O2. All that's going to happen here, once again, look out for that stereochemistry since it's a syn addition. It's this. And actually, the D could go here, or it could go here, and the OH could go here, or it could go here. And that's just because no matter where you put, they're both equally stable. So it could go either way. So this would also be correct. You don't have to draw both of them, but just to show you that these would both be correct. And you would not lose points if you did it this way, because there is no real difference. Those are either one could happen. Now, there are no enantiomers for this, though. Remember that, because of that stereochemistry once again. So let's go on to another reaction. I'm going to go over osmolysis real quick, just so you're prepared. The main thing to remember for these is O3 acts like a lightsaber and cuts the double bonds, replacing them with oxygen. So just remember these basically act like Anakin slaughtering the Padawans in episode 3. Or no, I think it's episode 4. That's one of the episodes. But just remember that. And the first example I have for osmolysis, aka O3, is something like this. And we're going to react this with O3. And now all you have to do here, cut it down the double bonds. Just cut the double bonds down the middle. And you're going to replace those with oxygen and then number them. So 1, 2, 3, 4, 5, 6. So you're going to have for 1, and on the other side you're going to have the same thing though. I drew that bad. And then count again. So we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yep. And then here we have 1, 2, 3, 4, 5, 6. So yep, that's your correct answer for that one. And all you do is cut it down the middle and replace those double bonds with O's. So now then, let's take a look at another one real quick. If you had something like this, all that would happen here, and we reacted this with O3. Let's put this down the middle. 1, 2. You would have O, and then you would have 1, 2, 3. Oh, that'd be your answer for this one. That's all you'd have to do for these. Not too hard. Quite simple. So the next one I'm going to go over are cyclizations. This is going to be the final thing we're going to go over. So cyclizations. Cyclizations, the thing to keep in mind for these is there's usually going to be an OH present, and it's going to be NaH or NABH. And all that NABH and NaH does is it protonates the OH so that it can then cyclize. So let's look at a few examples of this happening. So the first example is this. You're going to have Br. Like I said, you're going to have an OH on the starting group. And then you have this. And NaH and DMF. So what's going to happen here is this is going to leave you a positive carbocation. And now then we're going to erase this OH. It's going to get protonated and turn into O negative. So what's going to want to happen is a bond's going to want to be formed here. So now then all you have to do is number 1, 2, 3, 4, 5. So you're going to have a 5-membered ring. It's an oxygen. However, you have to remember that oxygen is going to attack from the back because that bromine left, and this is technically going to be kind of like an SN2 mechanism is how you should think of it. And then know that right here, if this is going to be 1, this is going to be 2, this is going to be 3, this is going to be 4, and this is going to be 5. So now then put that there. And that's all you have to remember. Actually, I think my bad. I did not do this right. You should have, I'm stupid, my bad. Should be here. There you go. And that's what that's gonna look like. So, pretty simple stuff. It's just, the tedious thing about these is marking the carbons correctly so that you know where the stuff is. Like, I even made that small mistake there real quick before I caught it. So just make sure you double check and it makes sense before you actually draw it out. So I have one more of these, and then I will leave you guys with that. So OH, Cl, Na, BH, and then we got DMF. So it's going to leave, it's going to give us a positive carbocation. It's going to get protonated, so go away. So once that goes away, it's going to become negative. It's going to want to attack here. So now then you're going to have 1, 2, 3, 4, 5. So you have another 5-membered ring. O here. You have that there. Then you're going to have this go there. This there. But once again, this is actually going to be a wedge. And that's your final product for this one. So I just want to thank you guys all so much for watching the video, and I hope these are helpful because it took a long time to write all this stuff out and just come up with some stuff to help you guys. And if there's any other questions, don't hesitate to message me on YouTube, Facebook, anything. I'm here to help. So I leave you guys with that. I hope you guys have a wonderful night and kick this exam's ass, guys. Don't forget to like